TON 618 is so large that ordinary space comparisons begin to fail. This is not just another black hole. It is one of the most massive ever discovered, a dark giant so extreme that it stretches the limits of human scale and forces astronomy to rethink what cosmic size really means. Tonight, the journey moves from the outer universe to the edge of this immense abyss. If this kind of deep space mystery belongs on the channel, please like the video, subscribe, and settle in. At the widest scale, the universe does not appear as a uniform field of stars. It arranges matter into an immense pattern of gathering and separation. Some regions hold many galaxies, while others remain thinly populated. Long filaments connect crowded knots, and between them lie vast voids where visible matter is sparse. This broad arrangement is often called the cosmic web, a simple name for the large structure traced by galaxies, gas, and the hidden gravitational framework associated with dark matter. Within that web, each bright galaxy is not an isolated island. It belongs to a wider pattern shaped over immense spans of time by gravity acting on matter that falls inward, merges, cools, and settles. TON 618 belongs first to this larger setting. Before it is understood as a quasar or as a black hole of unusual mass, it is one distant point within the universe's broad architecture. At this scale, familiar comparisons lose their usefulness. A star belongs to a galaxy. A galaxy belongs to a group or cluster, or drifts near one. Groups and clusters connect along structures so large that ordinary language begins to flatten their meaning. Even so, the pattern is not random. Gravity amplifies slight early differences in density, and over long spans those differences grow into the framework that later holds galaxies and the gas between them. The result is not a rigid lattice but a loose and changing structure, with motion everywhere. Some galaxies merge, some remain far apart. Some regions grow denser while others stay nearly empty. A source such as TON 618 enters human knowledge only as a faint signal carried across that immense setting. Brightness can mislead when the scale becomes this large. The most striking objects in the sky are not always the largest structures, and the most important influences are not always the ones that shine. Starlight marks where ordinary matter gathers into luminous systems, yet much of the cosmic framework is not directly visible. Dark matter does not glow, but its gravity helps shape the halos around galaxies and the larger scaffolding in which galaxies form. Gas also fills the space between galaxies and within groups and clusters, often thin, hot, and difficult to detect except through careful observation. The visible universe therefore has layers of presence. Some parts blaze, some parts remain dim, some reveal themselves mainly through motion. TON 618 occupies one tiny place in this layered setting, and the extremity associated with it does not place it outside the normal universe. It arises within the same broad rules that govern structure everywhere, though in a rare form carried far toward the upper end of what has been observed. At the outermost scale, even a giant black hole does not dominate the cosmos around it. This is an important correction to imagination. The phrase giant black hole suggests a presence that swallows regions of the universe like a storm crossing a landscape. Reality is quieter and more exact. Black holes influence their surroundings through gravity, but that influence weakens with distance. Their significance comes not from ruling the whole cosmos, but from concentrating extraordinary mass into a very small central domain inside a galaxy. From far away, the larger universe continues its wider motions almost untouched by any one black hole. TON 618 therefore sits inside the grand structure rather than replacing it. It is a local extremity embedded in a cosmos vastly larger than itself. That cosmos is also expanding. On the larger scales, galaxies tend to move away from one another as space expands. This does not mean every local system flies apart, because gravity can hold galaxies together in groups or clusters, but it does mean the broad canvas on which all structure rests is not static. The distances between major concentrations of galaxies change over cosmic time. Light crossing that expanding setting is stretched on its journey. Even without dwelling on measurements here, the main point remains simple. TON 618 belongs to a universe in motion, not a fixed celestial shell. It exists within an evolving cosmos whose large pattern opens outward while local gravity continues to draw matter inward. This combination of expansion and collapse gives the universe much of its character. Broadly, space opens. Locally, matter gathers. Clouds become galaxies. Galaxies distort, merge, and settle. Gas falls into deeper wells of gravity. Across enough time, the cosmic web grows richer in contrast. Dense places become more elaborate. Sparse places become emptier. The most extreme objects appear where matter has access to deep gravitational reservoirs and long histories of assembly. Yet at this outer level, restraint is important. TON 618 is not a break in physics. It is not an exception to the universe. It is an expression of the same physical order that shapes every other galaxy, only carried to a rare scale. Seen from this widest perspective, the name itself matters less than the setting. Human catalogues attach labels to points of light because the sky is full and memory is limited. The object called TON 618 enters those catalogues as a remote source among many others. What makes it remarkable is not its position in the sky alone, but the fact that one point in that map represents an active galactic center of exceptional power. Even that distinction becomes meaningful only against the larger background. Without the cosmic web, there is no galaxy. Without galactic assembly, there is no deep central reservoir of matter. The outermost region therefore provides the proper beginning. It removes the illusion that TON 618 is a lone monster floating in emptiness. Instead, it appears as one concentrated phenomenon within a universe already immense, already structured, and already far beyond ordinary human scale. The calmest way to approach such an object is to keep that scale in view. Astronomy often begins with a bright source, and then works outward toward context. But the mind understands better when the order is reversed. First comes the observable universe, with its filaments, voids, diffuse gas, hidden mass, and continuing expansion. Then within that setting come galaxies, and only much later the unusual centers some galaxies contain. In that widest frame, TON 618 takes its first proper place, not as an isolated wonder, but as a distant member of the largest known scene. TON 618 is not seen in the present condition in which it now exists. It is seen through old light. This is one of the quiet foundations of astronomy. Light does not arrive instantly from remote parts of the universe. It travels at a finite speed, and over great distances that travel becomes a journey lasting billions of years. For nearby objects, this delay is small enough to feel abstract. For a source as distant as TON 618, the delay becomes the central fact. The object enters observation not as it is now, but as it was when the universe itself was far younger than it is at present. At such distances, vision becomes a form of timekeeping. A telescope aimed at a remote quasar is not only gathering light from far away, it is also gathering a record from a much earlier cosmic era. The further the source, the deeper into the past the observation reaches. This does not mean the telescope travels backward through time. It means that the message carried by light is old when it arrives. The photons reaching Earth from TON 618 begin their journey long before human beings build modern observatories, long before Earth takes its current form, long before much of the later history of galaxies unfolds. The source is distant in space, and by that same fact it is distant in time. This relation between distance and age gives the sky a layered character. Nearby stars belong to a relatively recent visual layer. More distant galaxies belong to older layers. Extremely remote quasars belong to still earlier ones. The sky, therefore, does not show a single cosmic moment. It presents many different moments at once, mixed together by line of sight. TON 618 belongs to one of the older visible layers, a time when the universe is already rich with galaxies and already capable of producing very massive black holes, yet still much younger than it is now. Its light becomes a surviving trace from that earlier age. The expanding universe adds another feature to this ancient light. As space expands while light travels across it, the light is stretched. Wavelengths become longer. In astronomy, this is called redshift, a simple term for the shift of light toward the redder part of the spectrum as the journey through expanding space grows greater. Redshift is more than a change in color. It is a sign of cosmic history. It tells astronomers that the source is remote and that the light has crossed an expanding universe. By measuring this shift, they infer how far back in time the observed state of TON 618 belongs. The object is therefore dated not by direct access to its calendar, but by the aged condition of the light that reaches the telescope. This ancient view demands patience in thought. The name TON 618 may feel immediate when placed on a screen or in a book, but the reality behind the name is separated from direct human experience by an immense interval. The quasar state that astronomers study belongs to a past epoch. Whatever changes have taken place since then remain unseen in direct form. Observations indicate what TON 618 is doing at the time its light leaves, not what it is doing now in the present cosmic moment. This difference is not a flaw in observation. It is the normal condition of deep astronomy in most daily experience. Sight feels current. In the remote universe, sight becomes historical evidence. The earlier universe in which TON 618 is observed is not primitive in the simplest sense. It is not the first flash after the beginning, nor an age before structure exists. By the time the light seen from TON 618 begins its journey, stars have formed, galaxies have assembled, and heavy elements have already been produced in earlier generations of stellar life and death. The cosmos is active and structured. Gas moves through galaxies. Gravity reshapes systems. Black holes feed and grow. The universe at that time is younger, but it is not blank or unfinished. It already contains environments complex enough to support some of the brightest active galactic centers ever observed. Even so, age matters because the available time for growth is smaller. A giant black hole seen in an earlier epoch carries a different meaning from one seen closer to the present. The earlier the observed era, the less time the cosmos has had to build extreme objects. TON 618 is therefore striking not merely because it is large, but because the large state is seen in a universe that is younger than today's. This does not force the conclusion that the object is impossible. Observations indicate that very massive black holes can arise within cosmic history, though the exact details of the most rapid growth remain an active field of study. In this section, the important point remains temporal rather than mechanical. TON 618 reaches human knowledge as evidence from a younger universe. Its light also crosses changing environments on the way to Earth. It passes through intergalactic space, where matter is extremely thin, and through the broad expanding fabric of the cosmos. It survives this long passage well enough for its spectrum to be studied, its brightness measured, and its nature inferred. That endurance of information is one of astronomy's quiet achievements. Ancient light does not arrive with labels attached, yet careful instruments recover from it a history of motion, distance, and energetic activity. The farther the source, the more the observation becomes an act of reconstruction. There is calm value in this perspective. TON 618 is often described through its enormity, but before scale comes chronology. It is first an old signal. It is a reminder that the universe is not merely large but delayed in every direction. To look far is to look back. To measure a remote quasar is to study a preserved state from long ago. The object's importance therefore begins with its epoch. It stands in observation as a messenger from an earlier cosmic age, carrying within its stretched light the record of a bright and distant centre seen across billions of years of travel. A quasar is not a normal star and not a normal galaxy seen from afar. It is the intensely bright centre of a galaxy whose central black hole is actively feeding on surrounding matter. The word itself begins as a label for sources that appear almost star-like in early observations, because they are so compact and so distant, yet their light is far too powerful to be explained by a single star. In simple terms, a quasar is a galactic core in an unusually active state. Gas falls inward toward the centre, and before that gas is lost from view, it releases vast amounts of energy. The result is a small central region that can outshine the combined starlight of the host galaxy around it. This active state is not present in every galaxy all the time. Many galaxies contain central black holes, and evidence suggests that large galaxies commonly do, but only a fraction show the extraordinary luminosity that defines a quasar. Most galactic centres are far quieter. Their black holes may be feeding only weakly, or not in a way that produces a strong radiating core. A quasar, therefore, represents a special condition rather than an ordinary one. It appears when enough matter is available, when that matter reaches the central region efficiently, and when the release of energy becomes so intense that the nucleus turns into one of the brightest persistent sources in the universe. This brightness is the feature that first separates quasars from the wider population of galaxies. A normal galaxy shines through the collective light of its stars, with additional contribution from gas, dust, and sometimes regions of active star formation. A quasar is different. Its central engine dominates the visual identity of the object. The nucleus can become so bright that the surrounding galaxy is difficult to detect clearly, especially at great distance. What appears in a telescope is then not a broad stellar system with a clear shape, but a brilliant point-like source whose true nature must be inferred from its light. The quasar is therefore a galaxy centre, seen in a state of extreme radiative activity. Astronomers place quasars within a broader family called active galactic nuclei. This phrase describes galactic centres whose brightness is powered mainly by matter, falling toward a central black hole rather than by ordinary starlight. The family includes a range of activity levels and appearances. Some active nuclei are modest by comparison. Some are partly hidden by dust. Some aim powerful jets into space and are especially bright in radio wavelengths. A quasar lies near the strong end of that family, where the nucleus becomes exceptionally luminous. The key distinction is energy source. In an active galactic nucleus, The central region shines because gravitational energy from infalling matter is converted into radiation. That process is far more efficient than ordinary starlight in producing energy from a given amount of matter. For this reason, a quasar can be visible across astonishing distances. Its light crosses billions of years and still remains measurable. The nucleus is compact in physical size when compared with a host galaxy. Yet the energy released there is so intense that it becomes a beacon on a cosmic scale. This is why quasars matter so much in astronomy. They're not merely bright curiosities. They are markers of black hole growth, galaxy evolution, and the energetic history of the universe. Because they can be seen from great distances, they also reveal conditions in earlier cosmic eras. A quasar is therefore both a physical phenomenon and a tool of observation. Within that rare class, TON 618 belongs to the upper extreme. It is not notable simply because it is a quasar. Many quasars are already extraordinary by ordinary standards. TON 618 stands out because its luminosity and inferred central mass place it among the most extreme known examples. Observations show a source of remarkable brightness, indicating a nucleus powered at a tremendous rate. In the taxonomy of active galactic nuclei, this is not a mild or intermediate case. It belongs to the rare population where the central engine becomes so powerful that it challenges ordinary language of scale. Rarity matters here. The universe contains immense numbers of galaxies, and even a rare phenomenon can occur many times across such a vast population. Yet within the part of that population visible to human instruments, truly extreme quasars remain uncommon. Most galaxies are not quasars. Most active galactic nuclei are not among the brightest known. Most bright quasars are not placed as high as TON 618 in discussions of luminosity and central black hole mass. The object therefore occupies a narrow statistical region. It is not representative of galaxies in general, nor even of active galactic nuclei in general. It is an outlier within an already unusual class. Its outlier status does not make it mysterious in the sense of being beyond physical explanation. A quasar is understood in broad terms through well-established astrophysics. Matter falls inward. Energy is released. Radiation escapes from the surrounding structure before the matter crosses beyond visibility. Spectral features, luminosity, and variability help astronomers identify the phenomenon. TON 618 fits within that framework. What makes it remarkable is the scale at which the familiar quasar mechanism appears to operate. The same general process known from other active galactic nuclei seems to be present here, but carried into a regime of exceptional brightness and exceptional central mass. This creates an important shift in perspective. The term black hole often attracts attention first, but at this stage the object is better understood as a quasar, because the quasar is what observation actually presents. Human instruments do not see a black surface in space. They see intense emission from an active nucleus. The rarity is therefore first a rarity of radiance. TON 618 enters astronomical awareness as one of the most luminous known central engines, and only from that luminous state do astronomers infer the extraordinary properties associated with the black hole itself. In this way, the quasar category gives TON 618 its first true scientific identity. It is a distant galactic core in a violently bright feeding phase, a rare active nucleus whose output places it at the extreme, luminous end of the known population. Before its surrounding galaxy is clearly understood, before its mass is considered in detail, before its inner structure is described, It stands as one of the most uncommon things. The distant sky reveals a quasar so bright that it joins the highest ranks of known active galactic nuclei. TON 618 enters astronomy as a recorded source before it becomes a vivid idea in the mind. At the telescope, it does not announce itself through a dramatic shape. It does not appear as a swirling disk or a visible dark center. It arrives first as light collected from a small point on the sky, then sorted, measured, compared, and placed into catalogues. This is how distant objects become known in practice. A remote quasar is not discovered by looking at a clear portrait. It is identified through the disciplined reading of brightness, color, and spectrum, each one adding a layer of recognition until the source stands apart from the crowded background of the sky. The name TON 618 reflects that catalogue history. The label does not try to describe the object's nature, it simply marks its place in an observational record. Many astronomical names have this character. They preserve the origin of the listing rather than the physical meaning of the source. This can make extraordinary objects sound plain or technical, but the plainness serves a purpose. It keeps the first step of knowledge grounded in observation rather than in imagination. Before the object is discussed as one of the largest known black holes, it is first a source assigned a designation through survey work and later study. The label is modest. The reality behind it is inferred slowly from the light. At great distance, the sky compresses complexity into points. Nearby planets may show disks. Some nearby stars can be resolved in special cases. Some galaxies spread across the image with visible arms or central bulges. A distant quasar does not usually offer that kind of extended structure. Its apparent size on the sky is too small, and its central emission too concentrated for ordinary imaging to reveal much direct form. It therefore resembles a point source, something almost star-like in appearance. This resemblance is part of what once made quasars difficult to classify. They looked compact, yet their light carried signatures that did not match ordinary stars. The eye alone could not settle the matter. Only measurement could. Color begins that separation. Different astronomical objects distribute their light differently across wavelengths. A cool star, a hot star, a galaxy rich in old stars, a cloud of glowing gas, and an active galactic nucleus do not share the same balance of brightness from one band to another. Surveys that compare brightness in different filters can therefore flag unusual candidates. TON 618 belongs to the kind of remote active source whose light does not fit comfortably into the patterns of ordinary stars. Even before a detailed spectrum is taken, its measured colors help indicate that it is not a simple foreground object within the Milky Way. The source stands out because its light behaves differently. A fuller identity comes through spectroscopy, the practice of spreading light into its component wavelengths and reading the result as a structured pattern. In a spectrum, brightness is no longer treated as a single total. It becomes a landscape of lines and slopes. Certain wavelengths are enhanced by emission from hot gas. Others may be reduced by absorption. The overall shape may indicate a powerful energetic source rather than starlight alone. For a quasar, this spectral pattern is decisive. It reveals that the source is not a nearby star but a distant active nucleus, with gas responding to intense radiation in the central region. TON 618 becomes recognizable in this way. Its light, once dispersed and measured, carries the marks of a quasar. This method also overcomes the limitation of direct appearance. The telescope image may remain almost simple, a bright point on a dark field. but the spectrum is rich with physical meaning. It contains evidence of energetic gas, extreme luminosity, and great distance. It allows astronomers to distinguish between objects that look similar in a small image but differ completely in nature. A star and a quasar may both appear compact. Their spectra tell different stories. The star reflects the conditions of a stellar atmosphere. The quasar reflects an active galactic center powered by matter falling toward a central black hole. TON 618 is therefore pinpointed not by visible shape, but by the language carried in its light. Position on the sky also matters. Once the source is identified, astronomers fix its coordinates precisely enough for repeated observation. Different surveys, telescopes, and wavelength ranges can then refer to the same object. This continuity is essential. A remote source gains scientific identity when it can be found again, measured again, and compared across instruments and years. TON 618 is not one brief flash in a single observation. It becomes a stable entry in the astronomical record, a known location where a remarkable source continues to yield information. The catalogue name, the sky position, the measured spectrum, and the recorded brightness all join together into a durable identity. There is discipline in this process that helps keep scale under control. The object may later invite large comparisons, but its scientific life begins with patient classification. A source is noticed, its light is measured, its spectrum is examined, its position is fixed, its nature is compared with other known classes. Step by step, the record grows more precise. This gradual approach is especially important for distant quasars because they resist ordinary intuition. They are too far away to be experienced directly and too compact in the image to reveal themselves through obvious form. Only consistent observation turns them from points of light into physical objects with interpretable properties. TON 618 therefore becomes known as a specific source through the discipline of observational astronomy rather than through visual drama. It is found in the sky as a compact point, distinguished from stars by measured colour, identified as a quasar by its spectrum, and preserved in the scientific record by its coordinates and designation. The process is quiet, technical, and cumulative. It transforms a small patch of recorded light into one of the most remarkable active sources known. Yet at this stage, the object still remains what the instruments first encounter, not a visible giant, but a pinpoint whose light carries enough information to reveal an extraordinary distant core. Around TON 618, there is almost certainly a galaxy. But the galaxy is not what first claims attention. The central source is so bright that it overwhelms the surrounding starlight in observation. This is one of the recurring difficulties in the study of powerful quasars. The nucleus shines with such intensity that the broader system holding it becomes faint by comparison, like a dim structure lost in glare. In simpler cases, a galaxy can be studied through its shape, its stars, its dust lanes, and the spread of its light across the sky. In a source like TON 618, the host galaxy recedes behind the brilliance of the active centre. It is present as the larger home of the quasar, yet it is difficult to isolate clearly. This difficulty begins with contrast. A galaxy is extended across space. Its stars fill a broad system, and their combined light is spread over a larger area. A quasar nucleus is compact and concentrated. Even when the total galactic starlight is substantial, the central source can dominate what the telescope records because the energy is packed into a much smaller apparent region. The eye of the instrument is therefore drawn to the centre. the host becomes a faint background around a dazzling point. For very distant quasars, this problem grows stronger, because the entire system appears small on the sky, and the outer light becomes even harder to separate from the bright core. Observations indicate that the hosts of luminous quasars are generally massive galaxies. A central engine of such power is not expected to reside in a small and simple stellar system. The black hole, the surrounding gas supply, and the larger gravitational environment all point toward a substantial galactic structure. Even when the host cannot be seen in fine detail, the broader picture of galaxy evolution suggests a large and developed home. In the case of TON 618, astronomers infer the presence of such a host. But the central luminosity limits how much can be said with confidence about its exact visible form from ordinary observations. It remains a galaxy mostly known through necessity and context, rather than through a clear and quiet portrait. Distance adds another veil. The farther a galaxy lies, the fainter and smaller its outer light appears. Fine structures that might be distinguishable in a nearer system begin to blur into a faint envelope or disappear into background noise. Spiral arms, tidal distortions, compact stellar knots, or extended halos become difficult to resolve. A remote quasar host is therefore challenged twice. First, it is dimmed and compressed by distance. Second, it is buried beneath the concentrated brilliance of the nucleus. TON 618 sits in precisely this difficult observational situation. The galaxy around it is not denied by physics, but its visible character is masked by both remoteness and glare. This masking has consequences for interpretation. Astronomers would like to know whether the host shows signs of recent merger activity, whether it contains large amounts of dust, whether its stars are distributed in a smooth elliptical form or a more structured arrangement, and how its mass is divided between stars, gas, and dark matter. These are natural questions in the study of quasar environments, because a luminous active nucleus does not arise in isolation from galactic history. Yet for a source like TON 618, strong conclusions about the host's visible structure are limited by the dominance of the central light. Some properties can be inferred indirectly, but the direct image remains difficult. The host galaxy is therefore a haze in two senses. It is a faint outer presence around a brilliant centre, and it is also a concept partly blurred by incomplete detail. This should not be mistaken for ignorance of the basic framework. TON 618 is understood to lie in a galaxy because quasars are active galactic nuclei. The nucleus is not free-floating in intergalactic emptiness. It belongs to a larger stellar system that provides the wider gravitational setting and, over time, the supply of matter that can be directed inward. What remains uncertain is not whether there is a host, but how clearly its detailed appearance can be recovered from beneath the overwhelming central emission. There is also the question of dust and gas in the host. Galaxies are not made of stars alone. They contain interstellar material, sometimes cold and dense, sometimes diffuse and heated, sometimes arranged in lanes, clouds, or broader reservoirs. In active systems, this material matters, because it can both feed the central region and alter what observers see by absorbing or reprocessing light. For very luminous quasars, some of this surrounding material may glow in infrared wavelengths after absorbing energetic radiation. Even so, in the visible picture of a distant source such as TON 618, the host remains difficult to disentangle. The galaxy is a larger, more complex environment than the bright central point suggests, yet much of that environment resists direct visual separation. The faintness of the host also affects emotional scale. The name TON 618 often leads the mind toward the black hole alone, as though the whole object were nothing but a giant center. The dim host corrects that instinct, even while it hides. The quasar belongs to a galaxy, and the galaxy belongs to the wider cosmic structure already described. The brightness of the nucleus narrows attention, but the reality is broader. There are stars orbiting through the system, diffuse gas between them, dust grains mixed through colder regions, and a larger gravitational body holding the galaxy together. The host is not absent, it is simply overshadowed. Overshadowing is a common theme in astronomy, where the brightest thing in view is not always the whole story. A powerful nucleus can erase the quiet appearance of the system that supports it. In such cases, observation becomes an exercise in subtraction and patience. Astronomers try to model the bright central source, remove its contribution, and search for the weaker galactic light underneath. This work can reveal hints of the host, though not always with the clarity desired. For TON 618, the host remains difficult to display with confidence as a sharply defined structure. Observations indicate a massive galactic home, but the center radiates so strongly that the surrounding body is left subdued. This outer galactic haze is therefore the last broad veil before attention reaches the more crowded and energetic heart of the system. At the scale of the host galaxy, TON 618 is not yet a black hole or even merely a quasar point. It is a bright nucleus embedded in a larger stellar system whose outer identity is partly concealed by the light of its own center. The galaxy exists, holds, feeds, and frames the source, yet it remains dim beside the radiance that makes TON 618 famous. In the inner region of the host galaxy, the calm spread of outer starlight gives way to crowding. Stars are more numerous there, their average separation smaller, their collective light denser and more concentrated. Gas and dust also become more abundant in many active galactic centers, not always as a smooth medium, but as overlapping streams, clouds, and disturbed lanes shaped by gravity, radiation, turbulence, and orbital motion. TON 618 belongs to such an environment, even before attention reaches the immediate source of the quasar light. It enters a galactic heart where matter is packed more tightly, motions are faster, and the conditions differ from the wider and quieter body of the galaxy. The inner galactic region is not a single object. It is a domain of many components sharing the same broad gravitational well. Older stars may dominate some parts, moving in large numbers through the central bulge. Younger stars may appear where gas has recently cooled and condensed enough for star formation, though the details vary from one galaxy to another. Dust absorbs and scatters part of the light. Gas may remain cold in dense pockets, warm in diffuse clouds, or heated to much higher temperatures where activity is strongest. The central region therefore becomes layered and mixed. It is not empty space surrounding one bright source. It is a busy and structured environment in which many forms of matter circulate at once. Gravity shapes this domain from the largest visible scale downward. The mass of the galaxy draws stars into orbit and helps hold gas in the central regions, while local disturbances alter the exact paths that matter follows. Orbits near the center are generally shorter in duration than those farther out, because the distances are smaller and the gravitational pull stronger. Matter does not stand still there. It moves, crosses, gathers, disperses, and sometimes collides. Gas clouds may compress when they meet. Dust may trace cooler and denser structures. Stellar winds and earlier episodes of star formation can stir the medium further. The center of an active galaxy is therefore less like a fixed arrangement and more like a persistent state of circulation. This circulation matters because it helps set the conditions for central activity. Gas must lose some of its angular momentum, meaning some of the turning motion that keeps it on broader galactic paths, if it is to drift deeper inward. That loss does not happen everywhere equally. It depends on the shape of the gravitational potential in the galaxy, on interactions within the gas, and sometimes on larger disturbances such as galactic encounters or internal instabilities. In the central domain of TON 618, whatever the longer history may be, the present implication is clear. Enough matter reaches the inner regions for the nucleus to remain powerfully active. The crowded galactic heart serves as the reservoir from which deeper feeding becomes possible. The stars in this region are not passive decoration. Their gravity contributes to the central mass distribution, and their life cycles return matter to the surrounding medium. Aging stars shed gas. Exploding stars enrich their environment with heavier elements formed in earlier stellar interiors. Over time, the central region becomes chemically evolved, containing not only hydrogen and helium, but also richer material that affects cooling, dust formation, and the character of the interstellar medium. This means the galactic core is not simply denser than the outskirts. It is also often more processed by previous generations of stellar life. Matter there carries a longer history of transformation. Light behaves differently in such a region because so many sources and materials influence what escapes. Starlight from dense populations contributes a broad glow. Dust dims some wavelengths more than others. Emission from heated gas adds spectral signatures that reveal motion and temperature. Radiation from the active center can ionize nearby material, a term meaning that atoms lose some of their electrons under intense energy input, which changes how that gas shines. As a result, the central galactic domain becomes visually and physically complex. What reaches the telescope is not the simple sum of stars alone, but a blended record of stellar populations, intervening material, and the influence of the active nucleus on surrounding gas. In this environment, distance from the exact center still matters, even within the same crowded heart. Conditions become more extreme as matter lies closer to the core. Stellar density tends to rise. Orbital speeds tend to increase. Radiation from the active center grows more important. Gas may shift from relatively broad galactic structures into more inward-focused flows. Yet the region remains recognizably galactic rather than purely nuclear. Stars still move through it as members of the host galaxy. Dust and gas still reflect the broader ecology of the galactic center. The domain belongs to the inner host, not yet to the most compact engine itself. For TON 618, this inner galactic heart is especially significant because the scale of the central activity demands an abundant and persistent surrounding supply. A quasar of such luminosity cannot be understood as a lone object disconnected from its environment. The brightness seen across cosmic distance implies that large amounts of matter are available in the center over sustained periods. That availability begins here, in the crowded galactic domain where gravity, orbital motion, stellar evolution, and interstellar material all combine into a central reservoir. The host galaxy may remain visually subdued from afar, but within its heart there is no simplicity. There is accumulation, recycling, and continual motion. The region also places useful limits on imagination. Even near so remarkable a source, the galaxy does not dissolve into chaos. The physical processes are energetic, but they remain governed by the same principles that apply elsewhere in astrophysics. Matter responds to gravity. Gas cools or heats depending on local conditions. dust absorbs light, stars age and return material to space. The difference is one of degree and concentration. In the central domain of an active host, all these processes are crowded together and intensified by proximity to the nucleus. This makes the galactic core of TON 618 an essential threshold. It is the inner body of the galaxy gathered around the active center, dense with stars, threaded with gas and dust, shaped by fast orbital motion, and rich in the recycled products of earlier stellar generations. The outer host fades into this compact heart, and within this heart the conditions arise that allow the nucleus to blaze. At this level, TON 618 is still a galactic place before it is a more compact machine, a crowded central environment whose matter, motion, and density prepare the stage for the radiance at its core. At the center of TON 618, the nucleus becomes the ruling source of light. This is the region that gives the quasar its identity. The surrounding galaxy exists, the interstellar population exists, and the central gas-rich environment exists, but the nucleus dominates what observation receives from afar. In astronomy, an active nucleus means the compact central region of a galaxy, where extraordinary radiation is produced by matter moving inward under the pull of a supermassive black hole. The phrase sounds technical, yet the idea is direct. The center shines with unusual power because matter falling deeper into gravity releases energy before it disappears from view. This makes the nucleus different from an ordinary bright patch of stars. A dense star cluster can be luminous, but its light comes from many separate stellar surfaces. The active nucleus of TON 618 is another kind of source. Its brightness is concentrated, persistent, and tied to a central engine rather than to a simple population of stars. The energy arises because gas in the central region does not fall straight inward all at once. As it moves through the deep gravitational well, it is compressed, heated, and set into rapid orbital motion. In that process, some of its gravitational energy is converted into radiation. The nucleus glows because falling matter gives up energy on the way down. This conversion of gravity into light is one of the most powerful known energy-producing processes in the universe. Ordinary starlight comes from nuclear fusion inside stars, where light elements combine into heavier ones and release energy. The active nucleus works through another route. It draws on the depth of the gravitational well around the central black hole. Matter descending into that well can radiate with great efficiency before it passes beyond the region from which light can still escape. This is why a very small central region can rival or exceed the brightness of an entire galaxy full of stars. The nucleus does not need to be large in visible extent. It needs only a deep enough gravity field, enough infalling matter, and a structure that allows energy to emerge. The light from an active nucleus is also broad in character. It is not confined to one narrow band of the spectrum. Such nuclei can radiate across many wavelengths, from radio emission to visible light, ultraviolet light, X-rays, and beyond, though the exact balance depends on the structure and state of the source. This wide spectral reach tells astronomers that the nucleus is not a simple, cool body with one surface temperature. It is a layered and energetic region containing material under different conditions. Some parts are hotter, some denser, some more ionized, a word that means atoms have lost some of their electrons under intense energy. The nucleus is therefore not a lamp with one steady color. It is a compact environment whose radiation carries the signatures of many physical conditions at once. In TON 618, this central radiance becomes extreme. The quasar is known in large part because the nucleus is so luminous that it carries across a vast cosmic distance and still remains obvious to careful observation. That luminosity indicates a sustained release of energy on a tremendous scale. It does not suggest a brief flash like an explosion that quickly fades. A quasar nucleus is a feeding system that can remain bright over long intervals in astronomical terms, though its exact output can vary. The important fact at this stage is steadiness of power. TON 618 appears as one of the great long-burning central beacons of the distant universe. The brightness does more than reveal the nucleus. It transforms its surroundings. Gas near the active center absorbs intense radiation and responds by heating and glowing. Dust farther out may absorb some of the energy and re-radiate it at longer wavelengths. The nucleus therefore does not merely shine in isolation. It imposes an energetic condition on the nearby environment. Light from the center alters the state of surrounding matter, making the inner galactic region a place where radiation itself becomes an active force. This is one reason active nuclei are so important in galaxy studies. They are not only signs of central feeding, they can influence the gas around them and change how that gas behaves. Yet the brightness must be understood carefully. The black hole itself is not a glowing sphere. Light does not come from an illuminated surface of the black hole. It comes from matter in the central region before that matter crosses beyond visibility. This distinction is essential because the mind is tempted to imagine a black hole as a dark object somehow shining from within. In reality, the darkness belongs to the region from which no light escapes. The radiance belongs to matter outside that boundary, where motion, compression, and heating still produce escaping energy. The active nucleus is therefore a luminous neighborhood around the black hole, rather than the black hole itself becoming visible. Compactness also matters. The nucleus of a quasar appears small compared with a whole galaxy, yet its energy output is enormous. This contrast creates much of the astonishment associated with objects like TON 618. A galaxy spreads across tens of thousands of light-years or more, holding vast populations of stars. The nucleus occupies only a tiny fraction of that span. Even so, that tiny central region can dominate the total observed brightness. In the case of TON 618, this compact dominance becomes one of the main scientific clues. It shows that the source is not ordinary galactic starlight amplified by distance or confusion. It is a true active center whose power is concentrated at the core. There is also a certain order within this radiance. The light is intense, but it is not random. Its spectrum, its variability, and its overall energy distribution all reflect physical processes that can be studied. Astronomers read the nucleus through those patterns. They do not see its full structure directly, but the escaping light provides evidence of temperature, speed, density, and composition in the surrounding material. TON 618 therefore stands not only as a bright object, but as a readable one. The nucleus sends out more than brilliance, it sends information. At this inward stage, TON 618 is best understood as a concentrated engine of released gravitational energy. It is the active heart of a distant galaxy, a compact nuclear region wherein falling matter shines with such strength that the rest of the host is overshadowed. Its light crosses billions of years of space and still arrives as one of the most powerful signatures known from any galactic center, here in the nucleus itself. The quasar becomes fully present as a source of radiance, not a star, not the black hole alone, but the luminous central environment where gravity is turned into visible power. The immense scale associated with TON 618 is not measured by placing a ruler across a visible object. It is inferred from the behavior of matter near the center. This is how astronomy handles many distant systems. When direct size cannot be seen in simple form, motion becomes the guide. Light from gas in the active nucleus carries signs of speed, and speed carries signs of gravity. From that chain of evidence, astronomers estimate the mass of the central black hole. In the case of TON 618, this method leads to one of the largest black hole masses ever proposed for a known quasar. The key idea is simple at first. Matter moving under strong gravity tends to move faster when it is closer to a very massive center. If astronomers can determine how fast gas is moving in the nucleus, and if they can estimate how far from the center that gas lies, then they can infer the mass needed to hold that motion together. This is not the same as seeing the black hole directly. It is a measured inference from surrounding behavior. The black hole itself remains hidden, but the gas around it responds to the depth of the gravitational well, and that response is written into the light. Spectroscopy provides the crucial evidence. When light from the nucleus is spread into a spectrum, emission lines appear from gas that has been energized by the intense radiation of the active center. These lines are associated with particular atoms or ions, meaning atoms that have lost some of their electrons. In a quiet gas cloud, such lines would appear at relatively well-defined wavelengths. In a quasar nucleus, they often appear broadened. This broadening is a sign that the emitting gas is moving at very high speeds in different directions relative to the observer. Some gas moves toward Earth, which shifts its light slightly one way. Some moves away, which shifts it the other way. The combined result is a widened line rather than a narrow one. This is known as Doppler broadening, named for the shift in wavelength caused by motion along the line of sight. The broader the line, the higher the typical speed of the gas producing it. In active galactic nuclei, some of the broadest lines come from gas in what is often called the broadline region, a compact zone relatively near the central black hole where clouds or streams of gas move rapidly under strong gravity. TON 618 shows such broad emission features, and their width is one of the main clues that the central mass must be enormous. The light is not merely bright, it is shaped by very fast orbital or near-orbital motion in the nucleus. Speed alone is not enough. A small mass could also produce fast motion if the gas were extremely close. For that reason, astronomers also need an estimate of the region's scale. In many quasars, this is approached through empirical relationships that connect the luminosity of the active nucleus to the characteristic size of the line-emitting region. These relationships are built from more direct studies of other active nuclei, including methods that compare changes in the central light with later responses in surrounding gas. Once such scaling relations are established, they can be applied with caution to distant quasars whose inner regions cannot be mapped directly. TON 618 is studied in this broader framework. Its luminosity helps suggest a characteristic size for the line-emitting gas, and the observed line widths then provide the velocity scale. Together, they imply an extraordinary central mass. This approach does not produce a perfectly exact answer. It yields an estimate, and the estimate carries uncertainty. The geometry of the gas may not be the same in every source. The motions may not be purely circular. Some gas may flow inward or outward as well as orbiting. The observed angle can also matter because a flattened structure looks different depending on how it is tilted relative to the line of sight. For these reasons, astronomers do not treat a single mass value as a final and flawless number. They discuss ranges, assumptions, and systematic uncertainty. Even with those cautions, the conclusion for TON 618 remains striking. The inferred mass lies in the regime of tens of billions of solar masses, placing it among the largest central black holes associated with known quasars. A solar mass is simply the mass of the Sun used as a reference unit. Black hole masses in galactic centers are commonly expressed this way, because the numbers are otherwise too large for ordinary description. A black hole of a few million solar masses is already immense compared with stellar black holes formed from collapsing stars. One of hundreds of millions is larger still. One of billions belongs to the upper range of supermassive black holes known. TON 618 is placed beyond even that familiar upper range, in the territory where the mind begins to lose intuitive grip. It is not only a supermassive black hole, it is a candidate for an ultramassive one, a term often used informally for the very highest end of black hole mass. The strength of the inference comes from consistency between luminosity and line width. A quasar as bright as TON 618 implies a powerful central engine. Broad emission lines indicate gas moving at enormous speeds. When those facts are interpreted through the standard framework for active nuclei, the mass required becomes immense. This does not mean every detail of the nucleus is fully known. It means the black hole cannot be modest in scale. The observed behavior demands a central gravity field of exceptional depth. The exact figure may shift as methods improve, but the broad conclusion remains stable. TON 618 belongs among the most massive black holes ever inferred. There is a quiet discipline in this kind of measurement. The estimate does not come from spectacle. It comes from reading width in a spectral line, from comparing brightness with known scaling relations, and from accepting that light carries the imprint of motion. Astronomy often advances in this way. A seemingly abstract feature in a spectrum becomes a measure of speed. Speed becomes evidence of gravity. Gravity becomes evidence of mass. At the end of that chain stands a result so large that it reshapes the language used to describe the object. For TON 618 mass is therefore not a guess made from reputation. It is an inference built from the behavior of the active nucleus and the methods developed for quasars across many observations. Those methods carry uncertainty, but they also carry weight. They lead repeatedly to the same essential conclusion: the center of TON 618 contains one of the most massive black holes ever identified through quasar observations, so massive that ordinary astronomical scales begin to feel strained in its presence. Beyond the most compact center of TON 618 matter does not plunge inward as a loose rain falling straight into darkness. It approaches through a broader and more orderly structure. This feeding region is the outer accretion flow, the extended rotating supply of gas that settles around the black hole before moving further inward. The word accretion simply means growth by gathering matter. In this case, it refers to the gradual addition of gas to the central system. The outer flow is therefore the black hole's larger zone of intake, not yet the most extreme region, but already far removed from the quieter gas of the host galaxy. Here the inward journey becomes organized. Rotation is the first great shaping influence in this region. Gas arriving from the inner galaxy carries motion of its own. It does not begin at rest, and because it is already moving around the center, it cannot simply fall straight inward unless that turning motion is somehow reduced. This turning tendency is called angular momentum, a term for the persistence of orbital motion. In plain terms, matter that is already circling resists direct collapse toward the center. As a result, incoming gas spreads into a flattened rotating structure rather than diving inward all at once. The outer accretion flow of TON 618 forms because gravity pulls matter inward while rotation prevents a direct plunge. This produces a broad disc-like arrangement, Though it need not be perfectly smooth or perfectly thin at all distances, in the outer portions the flow may include denser streams, clumps, and irregular patches shaped by local disturbances in the gas. Some material arrives in uneven supply. Some parts may cool more effectively than others. Some regions may be stirred by shocks, turbulence, or changing illumination from the active nucleus. Even so, the overall pattern remains one of ordered rotation. Matter circles the center while gradually shifting inward over time. The outer accretion flow is therefore not a still ring. It is a slow conveyor of gas, always moving, always adjusting, always delivering material deeper into the nucleus. This region exists because the black hole is being fed on a sustained scale, rather than by a single isolated event. For a quasar as luminous as TON 618, the central engine requires a large and continuing supply of matter. The outer flow is part of that supply system. It acts as the transition between the larger galactic reservoir and the more compact radiating center. Gas that has already been funneled into the inner galaxy does not instantly become the brilliant quasar source. It first settles into this broader rotating structure, where inward motion becomes controlled and prolonged. The outer flow gives duration to feeding. It turns a chaotic arrival of gas into an extended process. Collisions within the gas help make this possible. Unlike stars in orbit, which can pass one another without often touching, gas is collisional. Streams can meet, compress, and exchange energy. Friction in the ordinary solid sense is not the right picture, but internal stresses, collisions, magnetic effects, and turbulent interactions all help the gas redistribute energy and angular momentum. One part of the flow can lose some of its orbital support and drift inward, while another part may take up extra angular momentum and remain farther out. This sharing process is essential. Without it, the gas would continue circling with little net inward progress. The outer accretion flow works because the gas can interact with itself. At this scale, temperature and density already begin to differ from those of the broader galactic medium. The gas is being gathered into a more compact region, compressed by gravity and exposed to radiation from the active nucleus. It may remain cooler in some outer zones and warmer in others, depending on local conditions, illumination, and the details of how matter arrives. The important point here is not the exact thermal state of each layer, but the fact that the flow is a physical environment with structure. It is not an empty orbital sketch. It is real matter arranged by gravity and motion into a persistent feeding configuration. Radiation from the nucleus can influence this region without fully stopping it. The quasar center is bright enough to push on surrounding matter through light itself, especially where dust or gas absorbs that radiation. Some material may be heated, ionized, or partly driven outward. Yet the continued existence of a luminous active nucleus shows that inflow still succeeds. The outer accretion flow of TON 618 is therefore not a simple river moving inward without resistance. It is a negotiated region where gravity draws matter in, radiation presses outward, and rotation keeps the structure spread into orbit. The balance is dynamic rather than fixed. This dynamic balance helps explain why a quasar can remain bright over long periods in astronomical terms. The black hole is not fed only by whatever crosses the last boundary near the center. It is supported by a much larger system of inward transport. The outer accretion flow stores, distributes, and gradually passes matter deeper inward. In this way, it acts like a reservoir in motion. Material entering the flow does not immediately vanish. It spends time in orbit, interacting with neighboring gas, losing some angular momentum, and migrating inward step by step. The quasar's power is therefore tied not only to the central black hole, but also to the health and scale of this surrounding feeding structure. The geometry of the flow also shapes what distant observers receive. A flattened, rotating structure presents different aspects depending on its orientation relative to the line of sight. Some views may expose more of the active center directly. Others may involve more intervening gas or dust along the path. This is one reason active galactic nuclei can appear different even when the same basic engine is present. For TON 618, the object is seen as a luminous quasar, meaning the central radiating region is not completely hidden from view. The outer accretion flow therefore belongs to the visible architecture of feeding rather than to a fully obscured core. There is calm order in this arrangement. The outer accretion flow is neither a random cloud nor an immediate fall into darkness. It is a broad rotating domain where matter learns how to move inward under the demands of gravity. Gas from the inner galaxy enters, settles, collides, redistributes motion, and slowly advances. The structure remains large compared with the deeper central regions, yet it already belongs to the black hole's direct sphere of nourishment. In TON 618, such a flow must be immense in consequence, because it helps sustain one of the brightest and most massive active nuclei known. At this stage of the inward journey, the object is best understood as a fed center, rather than only a bright one. Around the hidden black hole lies a rotating outer supply, broad enough to organize incoming matter, active enough to pass that matter onward, and stable enough in its overall form to keep the quasar alive across long spans of time. The light seen from afar depends on this quiet but essential architecture of inflow. Before matter reaches the deeper and more intense regions, it first belongs to the outer accretion flow, the great turning feeder that gathers the galaxy's inward moving gas and commits it to the central descent. Deeper within TON 618, the feeding flow becomes more compressed, more luminous, and more exact in its motion. This is the accretion disk in its stronger form, the region where inward moving matter no longer appears as a broad outer supply alone, but as a flatter, hotter, and faster structure wrapped around the central black hole. The disk is not a solid surface. It is a rotating body of gas, shaped by gravity and orbital motion, with each part moving under conditions set by its distance from the center. In this region, the release of energy becomes far more intense. The quasar's brilliance depends heavily on what happens here. Where matter still remains outside the hidden boundary, yet has already entered one of the most extreme environments in astrophysics. The basic reason for the disk's heat is simple. Matter falling inward through gravity loses potential energy, and that lost gravitational energy does not vanish. Much of it is converted into motion, compression, and heat. Gas in the disk rotates at very high speed, and neighbouring layers do not all move together at exactly the same rate. Inner portions orbit faster than outer ones because they lie deeper in the gravitational well. This difference in speed creates internal stress within the disk. The gas rubs and shears through magnetic and turbulent interactions, not as a rigid substance but as a fluid in continual differential motion. That internal struggle converts ordered orbital energy into heat. As the gas heats, it radiates. This is the foundation of the quasar's visible power. The disk does not merely transport matter inward, it shines because the moving matter becomes hot enough to emit enormous amounts of radiation before it disappears from view. In the outer disk, temperatures may be lower, and the emitted light may peak at longer wavelengths. Closer in, the gas becomes hotter, and the radiation shifts toward more energetic parts of the spectrum. The disk is therefore not one uniform glowing band. It is a thermal gradient, a layered field of rising temperature and rising radiative intensity as the distance to the black hole decreases. This gradient gives the accretion disk its physical richness. A distant observer receiving light from TON 618 is not seeing emission from one single temperature or one simple material state. The disk contains many annular regions, each contributing differently according to its local heat and speed. Some zones dominate the visible light, some contribute strongly in ultraviolet wavelengths. The innermost luminous regions may help produce even more energetic emission through related processes in surrounding hot material. The important point within this section is that the disk's brightness comes from distributed heating across a rotating structure, not from one isolated spot. The quasar shines through the combined radiance of many layers of inward moving gas. Motion in the disk remains orderly in the large sense and restless in the small sense. The overall pattern is rotational. Matter circles the black hole in nearly circular or slightly disturbed paths, while slowly drifting inward over time. Yet within that broader order, the gas is not calm. Turbulence develops, magnetic fields thread through the plasma, a word for gas so energized that electrons and ions no longer remain bound in ordinary neutral atoms. These fields can help transport angular momentum outward, allowing mass to move inward. This transport is essential. Without it, the gas would continue orbiting with little inward progress. The disk glows because it is not static. It evolves by redistributing motion inside itself. The speed in this region grows difficult to compare with anything familiar. Near the center of such a massive black hole, orbital velocities reach a large fraction of the speed of light. This does not mean all gas moves inward at that speed, but the orbital motion becomes extraordinarily fast. Each inner layer of the disk circles the black hole on timescales far shorter than those of matter farther out. The result is a deepening contrast between inner and outer zones. The closer the gas lies to the center, the greater the pull, the faster the rotation, and the more intense the heating associated with the stresses of flow. The disk is therefore a machine of gradients in speed, temperature, density, and radiative output. Density also changes inward. In the stronger part of the disk, matter is more tightly packed than in the broader outer flow, though not in the manner of a solid or liquid body with a sharp edge. Gas pressure, radiation pressure, and the geometry of the flow all matter. In highly luminous quasars, radiation pressure can become especially important. This means that light itself exerts a significant outward push on the surrounding matter. The disk of TON 618 is therefore not governed by gravity alone. Gravity draws matter inward, but radiation generated by the heated disk pushes back on the gas, altering thickness, stability, and the exact pattern of flow. The structure remains bound, but it is not simple. This balance between inward pull and outward radiative response helps determine how brightly the nucleus can shine at a given time. If too little matter enters the disk, the luminosity falls. If matter arrives in great abundance, the disk brightens, but the escaping radiation can also oppose continued inflow. A very luminous quasar, such as TON 618, suggests a system operating in a regime where both effects are strong. The disk is fed powerfully enough to radiate on an immense scale, yet the inflow remains effective enough that the brightness continues. The result is a sustained central blaze rooted in the ongoing conversion of gravitational energy into radiation. In this region, ordinary intuition begins to weaken. The disk is thinner than a galaxy and wider than any familiar engine. It moves faster than anything in daily experience and glows through processes that depend on deep gravity, rather than on combustion or simple heat sources. Even so, the physical picture remains coherent. Gas rotates, inner gas rotates faster, internal stresses and magnetic turbulence move angular momentum outward, matter drifts inward. Gravitational energy is converted into heat, heat escapes as radiation. That chain is enough to explain why the disk around a supermassive black hole can become one of the brightest continuous sources in the cosmos. For TON 618, this part of the system carries exceptional consequence because the inferred black hole mass is so large and the luminosity so extreme. The accretion disk must be vast in scale compared with the disks around smaller black holes, and yet the same principles apply. The system does not need new laws of physics to shine so intensely. It needs a sufficiently deep gravitational well, a high rate of inflow, and an accretion structure capable of transforming orbital stress into radiant output. Observations indicate that TON 618 fulfills these conditions in rare degree. Its disk becomes not merely a feeder, but the main visible furnace of the quasar. At this inward stage, the object is a rotating field of released energy. The accretion disk of TON 618 is hot, luminous, stratified, and fast, with each inner layer carrying matter deeper while radiating more fiercely than the layer beyond it. It is the region where gravity becomes visible as heat and motion becomes visible as light. Within its turning gas, the black hole's pull is translated into the brilliance that crosses the universe and reaches the telescope as one of the most powerful quasar signals known. In the innermost part of the accretion disk around TON 618, gravity becomes the dominant organizer of matter in a nearly pure form. Farther out, the disk still reflects some of the broader complexity of feeding, with uneven supply, changing density, and a stronger memory of the inner galaxy that sends matter inward. Here, much of that wider context falls away. The gas is now deep in the black hole's gravitational well. Its motion is set less by the history of where it came from, and more by the immediate demands of orbit under an immense central mass. This is still part of the luminous disk, still outside the hidden core itself. But it is the region where the disk approaches its greatest intensity, and where ordinary comparisons begin to lose their usefulness. The first change is in the strength of orbital control. Matter in the inner disk does not drift in broad leisurely paths. It circles in tightly packed trajectories, each ring of gas moving with extraordinary speed and with periods of revolution far shorter than those of the outer disk. The closer the material lies to the black hole, the more sharply gravity dictates its motion. In this region, the difference between one orbit and the next is no small matter. A slight decrease in distance inward produces a marked increase in speed and a corresponding increase in the energy that must be managed by the flow. The disk becomes a place of steep gradients, where conditions change rapidly across relatively small radial intervals. This steepness creates strain within the gas. Inner material races ahead of outer material. The disk does not rotate as a solid wheel. It rotates as a layered fluid, with each layer obeying the gravitational conditions at its own distance. That means neighboring zones are always sliding past one another. Magnetic fields, turbulence, and internal stresses bind the flow just enough to exchange momentum between those layers. This exchange allows some matter to move inward, while other matter effectively carries more of the turning motion outward. In the innermost disk, that process becomes especially intense because the speed difference between neighboring layers is so large. The gas is not only hot, It is dynamically stressed at nearly every moment. The heat produced here is correspondingly severe. Gravitational energy released in this inner region is greater per unit mass than in the outer parts of the disk, because the matter is descending into a deeper part of the gravitational well. As a result, the innermost disk becomes one of the brightest and hottest luminous structures associated with the quasar. The exact temperatures depend on the black hole mass, the feeding rate, and the internal physics of the flow, but the overall principle remains clear. As gas comes closer to the center, more energy is available to be released before the gas is lost from direct view. In TON 618, where both the black hole mass and the radiative output are immense, this inner zone carries an especially heavy share of the burden of brightness. This brightness does not mean the region is simple or smooth. The stronger the radiation becomes, the more it begins to influence the structure of the disk itself. Light exerts pressure, and in a very luminous quasar that pressure is not negligible. It pushes outward against the weight of the gas. The innermost disk is therefore shaped by a contest between the downward pull of gravity and the outward influence of the very radiation gravity helps create. Gas pressure, magnetic activity, and radiative transport all join the balance. The result is a structure that remains bound and rotating, yet is constantly negotiating its own stability under extreme conditions. The inner disk holds together not because it is quiet, but because its chaos is constrained by physical law. Density in this region is also hard to picture in familiar terms. The gas is compressed compared with the outer flow, but it is not compressed into a hard surface. It remains a fluid, partly ionized or fully ionized in many zones, threaded by magnetic fields and filled with particles moving at enormous speeds. The word plasma becomes especially appropriate here because the energy in the gas is high enough that electrons and ions no longer remain bound in ordinary atomic form. This changes how the matter responds to fields, how it transports energy, and how it emits radiation. The inner disk is therefore not merely hotter gas. It is an extreme plasma environment governed by gravity, electromagnetism, and radiative exchange all at once. At this depth, even the shape of possible motion becomes more restricted. Far from a black hole, gravity allows a wide range of orbits that can remain stable over long spans. In the inner disk, there comes a point where stable circular motion can no longer continue indefinitely. The gas can still orbit in an ordered way through the luminous part of the disk, but that order cannot be extended inward without limit. The innermost region of sustained disk motion lies close to the threshold where the flow must change character. Matter here lives on the edge of a transition. It still radiates, still circles, still belongs to the visible disk, yet it does so under conditions where stability is becoming fragile, and where a small further loss of support will alter the nature of the motion entirely. This fragility is one reason the inner disk is so scientifically valuable. Light coming from this region carries information about the strongest gravity available outside the hidden core. The emitted radiation can be shaped by rapid motion, high temperature, and the geometry of the flow. Spectral features from the inner disk may appear broadened and distorted by the combination of speed and gravitational depth. Observers do not need to see the disk ring by ring to understand that the inner region is special. The light itself reveals that the source arises in a domain where matter is moving fast enough and deep enough in gravity that familiar intuition starts to fail. In TON 618, the sheer scale of the central mass magnifies the importance of this domain, even though the same broad principles apply to smaller active black holes as well. There is also a growing separation between the disk and the rest of the galaxy in physical meaning. The outer galaxy still provides the long-term supply of matter. The broader host still frames the entire system, but in the inner disk, those outer conditions matter only insofar as they continue feeding the flow. The immediate behavior of the gas is now controlled by the black hole's local gravity and by the internal physics of the disk itself. This is why the inner region feels so detached from ordinary galactic language. It no longer resembles a stellar system or a dusty galactic core. It resembles a rotating gravitational furnace whose structure is defined by speed, depth, and heat. For TON 618, this inner furnace marks the point where scale becomes difficult even for astronomy's own categories. The system is still described with known concepts such as disk, orbit, radiation, and plasma. Yet each of those words is stretched by the extremity of the object. The black hole's mass is so large, and the central luminosity so intense, that the innermost disk becomes one of the most severe luminous environments nature can sustain. Here the quasar is no longer only a bright centre. It becomes a region where gravity rules with such strength that motion, heat, and structure all bow to it. Matter still circles, still shines, and still remains visible, but it does so under the nearest stable order that deep gravity allows. At the centre of TON 618 lies a boundary that gives the black hole its defining character. This boundary is called the event horizon. It is not a wall, not a shell of solid matter, and not a visible surface in the ordinary sense. It is the limit within which escape outward becomes impossible, even for light. Outside that limit, matter and radiation may still move through complicated paths under strong gravity. Inside it, all future motion leads inward. The event horizon is therefore not important because it looks like something. It is important because it marks a change in what the surrounding space allows. This change is easy to state and difficult to imagine. In everyday life, an object may be hard to leave because a force holds it in place. Yet some greater effort can still overcome that hold. A rocket can escape Earth if it reaches sufficient speed. A particle can leave a star if its motion is fast enough and directed outward. At an event horizon, this possibility ends. The gravitational structure of space-time, meaning the combined geometry of space and time under gravity, is so severely curved that every possible future path points further inward. The impossibility is not merely one of weak engines or insufficient energy. It is built into the structure of the region itself. For this reason, the event horizon should not be pictured as a destructive membrane waiting to tear matter apart on contact. Matter crossing it notices no hard impact from striking a physical surface. If the black hole is large enough, the crossing at the horizon itself may involve no sudden local shock at all. What makes the horizon profound is not a visible crash, but the fact that after crossing it, no signal can return to the outside universe. The boundary is silent. It does not glow by its own nature. It does not announce the crossing to distant observers through some bright flash produced by the horizon itself. The black hole remains black precisely because no light escapes from within. This is why the luminous quasar around TON 618 must be understood carefully. The tremendous brightness belongs to matter outside the event horizon. Gas in the accretion disk radiates while it still remains in the visible part of the universe. Heated plasma, rapid orbital motion, magnetic turbulence, and intense compression all help produce that radiance. The event horizon itself contributes no direct light. It is the central absence within the bright structure, the region that defines where visible participation in the outside cosmos ends. In a powerful quasar, the horizon is wrapped in brilliance but not replaced by it. Scale enters here with unusual force, because the size of the event horizon grows in direct relation to black hole mass. A more massive black hole has a larger horizon. For a black hole in the range inferred for TON 618, the horizon is not merely large by the standards of stellar black holes, it becomes vast by planetary standards. Observations and standard mass estimates imply a boundary whose span is immensely greater than the orbits of the familiar major planets around the Sun. The mind, accustomed to treating black holes as compact points, encounters difficulty here. TON 618 remains extraordinarily dense for its mass, yet the black region associated with it is enormous in absolute size. This does not make the black hole diffuse in the ordinary sense. Its mass is still concentrated into a domain whose defining feature is the horizon, and the gravitational effects near that region remain extreme. What changes is the scale of the invisible sphere. A stellar black hole may have a horizon measured in tens of kilometers. A supermassive black hole in a galactic center may have one measured in millions of kilometers. TON 618 goes far beyond such familiar stages. Its horizon belongs to a scale more often associated with broad reaches of planetary space than with single collapsed objects. The black hole is therefore both compact in one sense and vast in another. It contains an immense mass within a boundary that, by human standards, is itself enormous. There is a further consequence to this size. For a very massive black hole, the tidal difference in gravity across a small object at the horizon can be less severe than for a much smaller black hole. Tidal gravity means the change in gravitational pull from one side of an object to the other. Near a small black hole, that change can become violent already at or above the horizon. Near a much larger one, the horizon lies farther out in absolute scale, and the difference across modest distances can be gentler at the crossing itself, even though the black hole overall is far more massive. This is one of the quiet ways in which scale alters intuition. A larger black hole has a larger horizon, and the local experience at that horizon need not be as abruptly destructive as common imagination suggests. Even so, the event horizon remains a one-way limit. Its calm local crossing, if imagined in physical terms, does nothing to soften its deeper meaning. Once matter passes inward, no light from it can return. No later outward correction is possible. The horizon marks a true causal separation, meaning that events inside can no longer influence the outside world through ordinary signaling. This is why the horizon matters so much in physics. It is not just a convenient edge for drawing pictures. It is the boundary that defines the black hole as a region cut off from observational recovery. For TON 618, the extraordinary size of this boundary contributes to the object's reputation, but the reputation can easily become misleading if scale is discussed without care. The horizon is vast, yet it is not a giant vacuum mouth sweeping through the galaxy. The black hole's gravitational influence at great distance follows the same rules as any other mass. Stars orbiting far away respond to the total central mass, not to a magical sucking power. The uniqueness of the horizon appears only when matter comes close enough for escape itself to end. The size is therefore real, but its meaning belongs to local geometry rather than to some exaggerated force acting across the whole galaxy. The event horizon also gives the black hole a cleaner identity than the surrounding luminous structures do. The disk may vary, the feeding rate may rise or fall, the exact radiative output may change over time. The horizon remains the defining boundary through all such variations. It is the persistent inner limit around which the quasar's visible activity is arranged. In TON 618, where the luminous environment is exceptionally powerful, that hidden limit becomes easy to forget because the eye is drawn to what shines. Yet the true black hole begins not with the brightness, but with the horizon itself. At this inward stage, TON 618 is best understood as an enormous invisible boundary embedded within a blazing central system. The event horizon is not a surface of matter, not a luminous shell, and not a dramatic object in direct view. It is the silent limit beyond which escape from the black hole becomes impossible. In a system of such great mass, that limit reaches a scale that overwhelms ordinary planetary comparisons, while remaining entirely faithful to the same gravitational principle that defines every black hole. Here the quasar's light surrounds the place where light itself can no longer return. Close to the event horizon of TON 618, gravity no longer acts like the familiar pull that simply draws objects downward or inward through an otherwise unchanged space. It reshapes the very geometry in which motion occurs. In ordinary language, gravity is often spoken of as a force. Near a black hole, a deeper description becomes useful. Space and time are curved by mass and energy, and matter follows the paths allowed by that curvature. Around TON 618, where the central mass is immense, this curvature becomes severe in the near region outside the horizon. The result is not only rapid motion and intense heat in the surrounding disk, but also a profound alteration in how light travels, how clocks compare, and how nearby matter finds its path. Light in this region does not move as though space were flat and empty. A beam leaving one part of the inner environment can be bent by the black hole's gravity before it reaches a distant observer. This bending is not an optical trick caused by intervening glass or dust. It is a consequence of curved space-time itself. Paths that would be straight in weaker gravity become curved here. Around TON 618, some light emitted from the hot inner disk can be redirected, delayed, or sent along more complicated routes than ordinary intuition expects. In a calmer part of the universe, light often feels like the most direct messenger nature allows. Near a black hole, even light must negotiate the geometry. This bending can alter appearance in subtle ways. Parts of the inner disk may become more visible than simple flat geometry would suggest, because light from the far side can be curved around the black hole's vicinity. The exact visual pattern depends on angle, distance, and the structure of the emitting gas, but the principle remains steady. The black hole's gravity changes not only the motion of matter, but also the routes by which information escapes. A distant observer does not receive an untouched image. The received light has already passed through a region where gravity edits its journey. Time is also changed in this nearness. A clock deeper in a strong gravitational field does not keep time in the same relation to a distant clock as it does in weaker gravity. This effect is called gravitational time dilation. The phrase sounds abstract, yet its meaning is clear. Near the black hole, processes occur in such a way that, when compared with the distant frame of reference, time passes more slowly. This does not mean local physics stops. Matter in the inner disk continues to move, heat, radiate, and evolve according to the laws of nature. Locally, events unfold in their normal sequence. The difference appears when those events are compared with the timing measured far away from the strong field. Around TON 618, this distortion of time becomes significant in the inner region. A parcel of gas circling near the black hole experiences its own local progression of events. but radiation climbing outward from that depth carries the imprint of the gravitational field it escapes. Frequencies are shifted. Clocks do not agree across large differences in gravitational depth. The nearer the source lies to the horizon, the more strongly this effect matters. Thus, in the close surroundings of the black hole, not only space but duration itself becomes part of the unusual environment. Nearness is no longer just a matter of distance. It becomes a matter of living deeper in altered geometry. Light escaping from this region is affected in another connected way through gravitational redshift. As radiation climbs out of the deep gravitational well, it loses energy in the sense reflected by a shift toward longer wavelengths. This is not the cosmological redshift caused by the expansion of the universe across billions of light years. It is a local effect of strong gravity near the black hole. The deeper the light begins, the more the climb outward changes it. Around TON 618, this means that radiation from very near the center does not arrive unchanged. It emerges carrying evidence that it has struggled outward from one of the deepest wells in the observable universe. Motion close to the black hole adds another layer. Gas in the inner disk moves at enormous speed, and that speed combines with gravitational effects to shape the escaping light. Material rotating toward the observer can appear brighter in some circumstances, while material moving away can appear dimmer because motion alters the received radiation. In weaker settings, these effects may be small. Near TON 618, they become part of the fundamental appearance of the innermost environment. The result is that brightness, color, and timing near the black hole are all influenced by a union of rapid motion and severe curvature. The local world remains physically lawful, but it no longer resembles the gentle geometries of ordinary astronomical settings. Paths of matter are also constrained more tightly here. In the broader galaxy, many kinds of stable orbit can persist. Near the black hole, the allowed motions narrow. There are regions where circular paths remain possible and others where they do not. There are directions of travel more easily sustained and others that quickly lead inward. The geometry itself decides much of this. Matter close to TON 618 cannot choose freely among wide families of orbits. It lives in a landscape where the curvature of space-time has become one of the main architects of motion. The closer matter approaches the horizon, the fewer ordinary options remain for a rotating black hole. This near region may become even more intricate because space-time itself can be dragged around by the spin of the hole. This effect is called frame dragging. It means that the rotating mass does not merely sit within space-time and curve it. It also twists the local geometry in the direction of its rotation. Observations of TON 618 do not provide a complete direct map of this property, and it remains uncertain how rapidly the black hole spins. Even so, the theoretical possibility matters because it shows that nearness to a massive rotating black hole is not governed only by inward pull. The geometry may also acquire a preferred swirl, altering the motion of nearby matter and light. These changes in space and time do not make the region magical. They remain consistent consequences of general relativity, the accepted framework for gravity on these scales. What makes TON 618 remarkable is not that new laws are needed, but that known laws operate there in an extreme regime. The black hole's enormous mass creates a near environment where curvature, redshift, time dilation, and light bending all become practically important. Effects that exist faintly around ordinary stars become dominant features of the scene. Near the black hole, reality is not broken. It is simply brought into a deeper expression of its own structure. This is why the inner neighborhood of TON 618 cannot be understood through size alone. The great mass gives the system its scale, but the meaning of nearness is found in geometry. Space is bent. Time compares unevenly across depth. Light escapes along altered paths and arrives changed by both gravity and motion. Matter moves through a narrowing set of allowed routes shaped by strong curvature. In this region, the black hole is no longer merely a heavy center hidden behind the horizon. It becomes the organizer of a local world where the ordinary relation between distance, duration, and direction has been remade by gravity. A black hole as massive as Ton 618 does not appear through one brief act of accumulation. It grows by sustained feeding over long intervals, with matter arriving, settling, radiating, and passing inward again and again. At this depth of the subject, the central question is no longer what the quasar looks like or how the surrounding space behaves. The question is how such a vast black hole continues to gain mass. The answer begins with persistence. Growth on this scale requires not only a deep gravitational well, but also a long-lived supply of matter and a feeding structure capable of delivering that matter inward despite the resistance created by rotation and radiation. The black hole gains mass only from what finally crosses the event horizon. Everything outside the horizon may shine, orbit, heat, collide, and radiate. But none of that becomes part of the black hole until it passes the boundary of no return. This distinction matters because the quasar's great brightness is both a sign of feeding and a partial sign of loss. Matter in the accretion flow releases energy before it enters the hole. Some of the mass energy available in the inflowing gas escapes outward as radiation. The black hole, therefore, does not keep all that the surrounding flow brings. It grows from the remainder, the part that continues inward after the luminous process has already taken its share. Even with that loss, sustained inflow over long periods can build extraordinary mass. A black hole that is fed at a substantial rate over millions of years gains far more than one fed only briefly. Over tens or hundreds of millions of years, the difference becomes immense. Growth is cumulative. The added mass deepens the gravitational well, which can in turn support a larger and more luminous feeding system if sufficient matter remains available. The black hole and its accretion environment therefore develop together. The hole grows through the flow, and the flow is shaped by the pull of the growing hole. Ton 618 represents an extreme outcome of that long partnership between central gravity and continuing supply. One useful concept in this process is the Eddington limit, a term for the approximate balance point where outward pressure from radiation can counter inward pull on ionized gas. In simple language, if a feeding black hole shines too intensely, the light itself pushes strongly on the inflowing matter and can make further steady feeding more difficult. This does not create a hard and universal ceiling in every circumstance, because real accretion flows are complex and can exceed that balance for limited periods or under special conditions. Even so, the concept is helpful. It shows that black hole growth is not determined by gravity alone. The emitted radiation answers back, pressing against the very matter trying to fall inward. For a quasar such as Ton 618, this balance becomes especially important. The luminosity is enormous, which means radiation pressure must be significant in the inner flow. Yet the continued brilliance also shows that inflow is succeeding. Matter still reaches the center in large quantities despite the outward pressure created by the light. This suggests a feeding system operating at a very high level of efficiency in the practical sense of delivery. Though not all the incoming mass is retained by the black hole itself, the structure of the flow, The geometry of the gas, magnetic transport, and the long-term supply from the host galaxy all help determine how much material can keep moving inward under such conditions. The growth of a giant black hole also depends on continuity of supply from larger scales. The accretion disk cannot feed forever from nothing. Gas must continue to arrive from the inner galaxy, and before that from wider galactic reservoirs shaped by the history of star formation, stellar mass loss, inflow of cold gas, mergers, or internal instabilities. TON 618 therefore grows not only because its immediate disk is active, but because the larger galactic environment has delivered enough material into the central regions for extended feeding. The black hole is the final recipient in a chain of transport that begins far outside the horizon. Every stage matters. Gas must exist, move inward, lose angular momentum, settle into flow, survive radiative feedback, and continue its descent. Timescale is central here. A black hole does not need to be born near its final mass. It can begin from a much smaller seed and grow through repeated accretion over cosmic history. Observations indicate that some black holes in the early universe already reach great masses within relatively short cosmic times. And this remains an active area of study because the details of rapid early growth are not fully settled. For TON 618, which is observed in a younger universe than the present one, this question becomes especially relevant. Its existence indicates that black hole growth can be remarkably effective. Whether that effectiveness comes mainly from long periods of near-limit feeding, episodes above the usual balance, unusually massive initial seeds, repeated mergers, or some combination of these remains uncertain in detail. What is clear is that sustained acquisition of matter is able to build a black hole to extraordinary scale. Mergers may also contribute. When galaxies merge, their central black holes can eventually form a pair and, under the right conditions, combine into a larger black hole. Such events do not replace accretion as the main luminous process of the quasar, but they may add to long-term mass growth across cosmic time. Observations of TON 618 do not provide a complete historical record of all such past events. It remains uncertain how much of its mass comes from smooth feeding, and how much from earlier black hole mergers. Still, within the current active state, the continuing increase in mass depends on accretion now. The black hole grows because matter is crossing the horizon in the present feeding phase visible through the quasar light. There is a quiet paradox in this. The more effectively the black hole is fed, the more intensely the surrounding matter shines, and the more that radiation can resist further inflow. Growth on the larger scales is therefore not a simple uninterrupted fall. It is a regulated process, always negotiating between supply and resistance. Too little matter, and growth slows. Too much radiative pressure, and inflow can be hindered. The black hole grows best when the surrounding environment can keep sending matter inward, while the accretion flow remains stable enough to continue transporting it all the way to the horizon. TON 618 suggests that such a balance can be maintained at a very high level for substantial durations. At this stage, the giant black hole is best understood not as a finished object frozen in size, but as a continuing act of accumulation. Its mass reflects the integrated result of long feeding, repeated inward transport, and successful passage across the horizon by enormous quantities of matter. The quasar's radiance is the visible sign that this growth is underway. Gas arrives from the galaxy, enters the accretion flow, loses angular momentum, heats, shines, and then, in part, vanishes into the black hole itself. Through that persistent inward transfer, carried on over vast stretches of time, TON 618 reaches the immense scale inferred from its light. Its growth is not sudden. It is the patient work of gravity sustained. TON 618 ultimately matters because it presses against the upper end of known black hole scale and forces astronomy to examine what those limits really mean. A black hole of such inferred mass is not important merely for being large in a numerical sense. It is important because it tests the ability of accepted cosmic processes to build and sustain an object so extreme. When astronomers describe TON 618 as one of the most massive black holes known, they are not only placing it in a ranking, they are identifying a case that helps define the observable range of black hole growth. The object becomes a measure of how far nature appears able to carry the union of gravity, galactic feeding, and cosmic time. In this sense, scale is not an ornament placed on the object from the outside. It is the scientific content. A black hole of modest supermassive size already shows that galaxies and central gravity develop together. A black hole in the range proposed for TON 618 pushes that idea into more demanding territory. It suggests that the link between galaxy evolution and black hole growth is capable of producing outcomes far beyond the ordinary central masses found in many large galaxies. The object therefore sharpens an existing picture rather than replacing it. It shows that the same general framework of inflow, accretion, feedback, and long-term assembly can operate on a scale so large that common comparisons begin to lose clarity. This loss of clarity is itself part of the meaning. Human thought often relies on scale by comparison. A mountain is compared with a building. A planet is compared with a star is compared with the sun. These habits remain useful until the object under discussion becomes so extreme that the comparison clarifies one feature only by hiding another. TON 618 can be compared with planetary orbits, with the scale of the solar system, with more familiar black holes in galactic centers, or with the sun itself in mass. Each comparison reveals something, yet none can hold the whole reality at once. The mass is too large for ordinary stellar language. The horizon is too large for ordinary black hole language. The luminosity is too strong for ordinary galactic language. This is why the object feels as though it breaks scale. It does not break measurement. It breaks the ease of intuition. Astronomy encounters this difficulty often, but TON 618 offers a particularly clear case because several extremes coincide in one source. The black hole mass is inferred to be enormous. The quasar luminosity is immense. The event horizon reaches a span that overwhelms planetary habits of thought. The object is seen in a younger universe, which adds pressure to the question of growth. None of these facts alone would make the source so arresting. Together they produce a system that occupies a rare part of parameter space, meaning a rare combination of physically important properties. TON 618 therefore becomes valuable not only as an isolated marvel, but as a marker of the most expansive conditions black hole astrophysics must be prepared to explain. It also reminds astronomy that upper limits are often provisional. The phrase "one of the largest known" does not mean the largest that can exist in principle, nor does it mean that observation has found the final boundary of black hole mass. It means that within present surveys and accepted estimates, TON 618 lies near the highest end yet identified. This distinction matters because the observable universe is vast and incomplete in coverage. Some extreme objects may remain undiscovered. Some mass estimates may be refined. Some sources now grouped together may later separate into more precise categories. TON 618 is therefore both an achievement of current observation and a sign of what remains open. It defines the present frontier without claiming to close it. Theoretical understanding is also tested here. Standard black hole physics, accretion theory, and general relativity remain applicable. Yet the object invites closer scrutiny of how these ingredients combine over cosmic time. The details of rapid growth at the highest masses remain uncertain. The relative roles of prolonged feeding, early seed mass, and mergers are still studied. These are not signs that the object lies outside accepted science. They are signs that accepted science still contains active edges where observation and theory continue to refine each other. TON 618 serves that refinement by occupying one of the most demanding known cases. The object also helps place human scale in proper relation to cosmic scale. In daily life, size is tied to touch, distance walked, volume occupied, and time directly felt. None of these measures survives intact near TON 618. The black hole cannot be pictured accurately as a hole in the ground, a mouth, a drain, or a sphere like a planet. Those images are too small in one sense and too concrete in another. What exists there is a gravitational domain of enormous mass, invisible at its core, wrapped in radiating matter, and defined by geometry more than by surface. The human mind can understand this in formal terms, but it does not inhabit such scales naturally. TON 618 therefore becomes a lesson in humility. It shows that the universe is not obliged to remain within the bounds of familiar imagination, yet it also shows the reach of disciplined understanding. Human senses alone cannot grasp such an object. Instruments detect its light, spectra reveal motion, theory connects motion to gravity, gravity implies mass. Mass sets the scale of the horizon and the depth of the well. Step by step, a source that begins as a remote point is translated into a physically meaningful reality. The scale overwhelms intuition, but it does not defeat reason. In the end, TON 618 stands as a boundary object in modern astronomy, not because it ends inquiry, but because it shows where inquiry becomes most exacting. It marks the high terrain of black hole growth, where galaxies, accretion, radiation, and relativistic gravity converge at uncommon magnitude. It demonstrates that the universe can gather matter into a central darkness of extraordinary extent, while surrounding that darkness with one of the brightest sustained engines known. Its true significance lies there, in the measured tension between invisibility and radiance, between comprehensible law and overwhelming scale. TON 618 does not break the structure of the cosmos. It reveals how immense that structure is allowed to become. The distant light of TON 618 reaches the telescope after a journey so long that the object enters thought as both place and past. It remains a quasar in an earlier universe, a bright centre surrounded by layers of matter, motion, and gravity that grow more concentrated toward the unseen core. Around it, the larger cosmos continues its quiet expansion. Galaxies keep their patient motions. Gas drifts through wide, dark intervals. Light crosses those intervals slowly, carrying old states forward into the present moment of observation. At the centre of that long journey rests a black hole of such scale that ordinary comparison becomes thin and uncertain. Yet the physical picture remains calm. Matter falls inward. Motion becomes heat. Heat becomes light. Light escapes from the last visible regions and travels across the universe. Beyond that visible radiance, the event horizon remains dark and silent, holding the final inward path where return is no longer possible. Nothing in this picture requires excess or drama. The enormity is already present in the measured facts. Ton 618 therefore settles into astronomy not as a mythic object, but as a natural one, though natural on a scale far beyond daily intuition. It belongs to the same universe that forms stars, gathers galaxies, and bends light through gravity. It follows the same laws, but in an extreme domain where those laws reveal their deeper reach. The mind approaches it by stages and finds that even the most immense structures remain shaped by quiet principles: gravity, motion, time, and light. In that sense, the object leaves behind not noise, but proportion. It places human thought gently inside a cosmos that is older, larger, darker, and more orderly than immediate experience suggests. Far from Earth, far back in time. Ton 618 continues to shine through the matter around its hidden centre, and its light continues to arrive as a calm reminder of how vast the universe already is,